Good afternoon, and welcome to the final session in the molecular imaging track. Thank you for coming and sticking out to the bitter end. Those of you with sharp eyes may have noticed there's actually no title for this session, and that's because this is MI6. That's Her Majesty's Secret Intelligence Service. So if I told you the title of the session, I'd have to eliminate you. Anyway, without further ado, I'm very happy, very delighted to be able to introduce the first speaker, Professor Lee Dong-soo from the Department of Nuclear Medicine at Seoul National Hospital and University. And he is actually a pioneer in the field of radio nanomedicine. And so we look forward to hearing from him on the use of nanoparticles and nuclear medicine.
Okay, thank you, Chairman. And during this talk, I'll touch upon the use of nanoparticles and their possible use for nuclear theranostics. Actually, I was given the title of the nanoparticles, so I tried very hard to focus on nanoparticles. But as a clinician and physician, actually, I'm not interested in particles. I'm interested in using those. So the nanoparticles and their possible use is going to be emphasized. This attempt belongs to the field of radio nanomedicine. That's combined nuclear and nanomedicine. So in radio nanomedicine, we can use the trace amount, and also tracer kinetic is going to enlighten us using our well-known the equipments. Nanoparticle size here, the salicylic acid size, and also the here the albumin size, and then antibody. Everybody is just kind of call it antibody, but antibody is just a nano-sized, 10 to 15, and gold nanoparticle 20, or the recent iron oxide is just 5 nanometer. That's the size issue. And regarding the materials, because we are using the nanomaterials, and we can use the exogenous radio labeled nano materials, inorganic ones such as the iron oxide, or organic materials and traditionally liposomes. Recently, there has been a boom of the endogenous ones and extracellular vesicles, which is often called the microvesicles or the exosomes. Exosomes are the quite familiar term. So if we just label those nanostructures, nanomaterials, or nanoparticles with the radionuclides, then we can just do the nuclear theranostics with radio nanomedicines. Let me just talk about later. I just changed this. Even though this is MI6, I'm more interested in MT6 and therapy with targeted delivery. Everybody is saying that pure theranostics. I have been in the imaging business for the past 28 years. Before that, I was an internal medicine physician. So now the VISTA point, to avoid confusion. Nanomedicine is using radio nanomedicines. Just like that's drugs. If plural is the drug and radio nanomedicine is what we are doing, we have just to change it from small molecules, which is quite capable of the active targeting. You know, the glucose and galactose and mannose are only the hydroxyl residues position is different. But their brain tumor heart and hepatocyte or Kappa cells all are different. Or antibodies, which is well known for their the affinity and even avidity, but antibodies or recently developed peptides and macromolecules, we are not sure they are really active targeting agents or not. So there has been a dispute. And so the nanoparticles position is just a small molecules and peptides and macromolecules and their nanoparticles and combination of those. What I mean is just nanoparticles, bare nanoparticles are not the impressive. It just should be surface. They call it, chemists call it surface modification. We can just call it okay. This is the nanoparticle here. If you just put pegylation here, or the microRNA can load it, or anybody can also load. So these are the nanomaterials I have personally used for the last decade. Oh yeah, it's decade. I just started my nano studies 2009 when I visited this PostTech, which is a Southern technology, very good technology, the college and university. So I just discussed with the chemists or chemical engineers there. That was the first. It's almost 10 years. And since then, we just were interested in using this for in vitro use or the for endoscopy use, surface enhanced Raman, or even in vivo use of convergent nanoparticles. So while just trying to understand the in vivo behaviors of those nanoparticles, whether modified or not, in the literature, I found that they were said to be captured by reticular endothelial system, or which is also mononuclear phagocytic system. MPS is the most recent term. Just to if the site ref several, and here you can find the liver spleen and 24-hour, 20. So as a in vivo experts, we need to just to meticulously analyze these, not all these. These papers, I'm not just blaming, I'm going to blame a group of scientists, chemists. They are just kind of making hype. Their nanomaterials are very good for medical use. My heart is sunken. there are such a huge gap and death belly. So the first question is just those, even sometimes toxic. The quantum dot is cadmium 1. So can it decrease the amount of nanomaterials using radio nanomedicine? Yes. And let me just the site. We are giving the patients Tylenol, oxycodone, 500 milligram. I was surprised that because I'm out of the business of radiology, our radiology colleagues are giving to the patient, and here Magnavist 6 gram. I think as a physician, I think that's the cause of the nephrogenic systemic sclerosis sometimes happening in patients. And in case of MIBI, we are using the 100 microgram, and in case of new compound net spot at 40 microgram. So when I looked for the FDA guideline here, we can just do the microdose study when a small molecule is 100 microgram. However, in case of the peptide or proteins, they say that 30 nanomoles. And in case of nanoparticles, when I consulted Korean FDA, they, for the time being, they think that nanoparticles can be considered as like a peptide. So using Avogadro number, the 10 to 16 nanoparticles can be given. So we were interested in, and 70 kilogram of human and 30 nanomole is going to be, in case of the mouse, it's just 100th. So less than 100th is 300 picomole. So we just decreased. 50 picomole is the largest one here, and 1,000th here, 0.05 picomole. We were interested in whether that kind of a small amount is going to represent the behavior of the huge amount of nanoparticles. So you can find here gallbladder, all those gallbladder. So it means that they are taking the same route, and tracer principle worked. That's my the interpretation. Then the second question, I'm going to ask several questions, and I'm going to answer to that. Can we follow the biodistribution with this? This question is going to rephrase that integral ones can be followed. Isn't there any kind of issue of metabolites or fragments in case of small molecules and peptides respectively? Yes, but not always. We need to check. So during that time, when I was interested in that one, the German group had studied this, whether the encapsulated nanoparticles and with label, radio label, are going to be just this kind of disencapsulation or its integral. And they correctly concluded that the blood and here the indium was labeled for the capture and the gold was labeled, radio gold was labeled for the core. So they could correctly conclude that it's being excreted as a detached form. So it means that you are seeing only the capture. The gold is somewhere else. However, it was published in Nature Nanotech, and without knowing their study, we used a UCNP conversion nanoparticles and labeled, and imaged and quantified, and conversion luminescence imaging and PET. We found that all of our nanoparticles are excreted as an integral form. So it was accepted. And integral form. We even fishes PET and fishes ULI, conversion luminescence imaging, and counted. That was a laborious job. And after that, the finding that I looked again the literature, and there has been several image reports, and the chemists did not describe very well, but interestingly, after 24 hours, the intestinal activities are all there, or liver activity was gone, spleen activity remained. It means that in addition to RES, there is the mechanism of hepatobiliary excretion here. So in vivo stability, here is an episode. Chinese Society for Nanomedicine has just inaugurated several years ago. I was an invited presenter, and also interestingly, the German group's leader, Wolfgang Park, was there. We just presented each other's. I was presenting the scientific reports. He was presenting a more prestigious Nature Nanotechnology. His one was disintegrated, and ours one was integral forms. So we were puzzled. So after the work, we thought that if we use the thiourea, this is just kind of there. If they use the amide, then it might be the disintegrate. That kind of issues should be. What I'm saying is just not ours are superior. It's just we need to check. And then the next issue is excretion predictable? There was a very good paper from Harvard in Nature Medicine or a while ago. So size alone matters, and Professor Dr. Choi emphasized that, and he did a comprehensive study. So size alone matters? No. Let me explain why. After his the publication, there has been a lot of interest by the materials scientists. So in these Nature review materials or those eminent journals, they started to review here. And liver and kidneys are the excretion, the organs. And kidneys, yes, the size matters. However, the shape sometimes matters. Or even in this case, cyclodextrin is metabolized in the glomerular basement membrane. It was really interesting, and these investigators correctly set up the kinetic modeling, and they did solve and found out this one and confirmed with the invasive study. So this was the first one that I just found here. That UCLA and Caltech leaders, they did use the copper at the time and siRNA for therapeutics. And pharmacokinetic was analyzed with our method, and pharmacodynamic, actually, dynamic action was by this molecular imaging method, and they correctly concluded that nanoparticle is secured or captured by the tumor site by enhanced permeability and retention. That's kind of kinetic. And ligand is helping here, the transferrin. That's our domain. the next issue is can we control excretion and biodistribution? Actually, can we control excretion and biodistribution? Now you can just imagine, because I have enough time. So answer would be yes or no. Of course, yes. Yeah. Surface but the question can be rephrased. Surface modification is so easy even as to go to clinical trials. So we are not doing the hobby experiment. So, and we did a kind of upright. If we put the antibody can be like this, but it should be upright, or should be very mild. The core materials are harsh. It maintains its the characteristics, but the antibody or peptides or other nucleic acids are so subtle, so fragile. So that's a click reaction. So, but this was in vitro. But however, for in vivo, there has been since I just heard from my chemist colleagues, radiochemist colleagues, that there has been a kind of a boom of a study in our radiopharmaceutical science symposium, the bioorthogonal and click. So here, the blue color is a click reaction, and all are alkyne and azide, alkyne, octine, and azide, and the cycloaddition process. But in this case, the copper presence or copper absence, and in copper absence, much more they're friendly to the peptides or the labeled the macromolecules. So they did just to summarize that. This was so with this kind of the chemical method, we can just label, surface modify. However, there is another attractive method, which is the simultaneous physical labeling. So it's just encapsulation. Using that physical labeling, we have a lot of space. So we can just combine lutetium and the gallium with the same molecule, same particle, and lutetium and yttrium and the combined therapy. Or I'm not quite sure, the actinium or something. So sometimes it can just be multiplexed, clicking, and RI pre-labeled chelator. So that's kind of a making nano platform. Radioisotope pre-labeled one is just in the vial and then mix and then injection. That's our dream. Okay. So that what kind of mechanism is working in encapsulation quantum dot? It's just a pre-made micer and also quantum dot, just mixing, vortexing, and column chromatographies. That's it. So that was published back in almost 10 years ago now. And it was also applied for iron oxide nanoparticle and UCNP here. So now we can do surface modify with pegylation and control pharmacokinetic and examine the biodistribution with trace amount. Okay, nanoparticles, if you give them too many amounts, and it will be immersed. So do they know? So then oncologists or our biopharma companies experts, they do know the biodistribution of small molecules and peptide and antibodies? I think not. So the small molecules here, doxorubicin. When I was a resident in internal medicine, I just gave many doxorubicin, cisplatin, and patients suffered. So since then, they have changed it to tyrosine kinase inhibitors and monoclonal antibodies. Still, they suffer. Why? Because pharma companies, they are aiming at the blockbuster. Blockbuster means they need to lower the 19 to 15 to 12, or then they sell more. So we all know that. So oncologists know those are toxic, and the kind of the many benzene rings are going to lead them to the anywhere. Or sometimes they are interested in pegylation and this kind of enzymes or the cytokines. They all have only once injected, minutes of half-life. We cannot use that, so they have pegylated. So pegylation is just kind of already FDA approved. So that was the story of the exogenous ones, which I think the chemists had made a hype. So among the hypes, I tried very hard to choose to be used for in vivo. So then what about the endogenous radionanomedicines? It's about the using exosomes and extracellular vesicles. When I first presented, one of the eminent molecular imaging experts from Stanford was in the audience during lunchtime. He abruptly asked me, "Do you think that exosomes can be used for therapy?" So that was the first time I started to think about that. And yes, maybe. And why? Because we have a long history of understanding how to use the liposome. Liposomes are already used for delivering to doxorubicin, adriamycin, just to saving heart. When I was a resident, we did gated blood pool scan so much time for the doxorubicin patients. But now, after the introduction of the liposome, the doxorubicin regimen, but interestingly, if this is a morphine, and this can be considered as an endorphin, okay? So this is endogenous one. Interestingly, exosome, knowledge about the exosome has just kind of recently exploded. So we try to label them with our method. And inoxide, they are using that, and reporter sometimes and lipophilic fluorescent dye. So radio labeling scheme was like that, and scientific reports. This was first they submitted to JNM. JNM reviewers just turned it down. The reason was it's too simple. It's self-evident. It does not consist any the paper. So we just submitted to other journal. So that's HMPO is just going into the exosome and then became hydrophilic. It's trapped and can be just a cell labeling, like cell labeling. And this is a technetium HMP exosome labeled the technetium HMPO labeled exosome. Okay, so you could just find the here whereabout, and even you can find here. At first, we did not notice, and here lymph nodes. Why? Because that exosomes were derived from the macrophage cell line. Human neural stem cells, the similar the excretion. However, we could not see any one. So there is a difference. And every cell is excreting exosomes, and every cell is receiving. But the field exosome, there has been a society of the International Society of Extracellular Vesicles that they have started, and they are publishing in Journal of Extracellular Vesicles. And extracellular vesicles is a kind of prodigy, a future prodigy by the Sam Gambier. We listened to the Sam Gambier in this morning plenary lecture. So the many people, many the companies are interested in using that. So, however, there is no way to discriminate which subtype and which and that kind of. It's kind of almost 100 years ago, endocrinology would have been like that before the radioimmunoassay has been introduced by our ancestors. Okay. And then let me just the almost final. There has been a report that usually the exosomes are labeled with fluorescence dye. Here, DII. However, once exosomes are disintegrated, that fluorescence dye, what's the fate of the fluorescence dye? It's recirculated again and again and again. So we could find here brain uptake, but we could not find any technetium HMPO labeled the uptake. So I can even say, that the fluorescence-labeled exosome biodistribution is all bogus. Should I prove that? No, I don't have time. So this is for nuclear medicine theranostics. This is the combination of the idea, and because we have a lot of surface there, we can just label lutetium, or we don't actually. And all this was, and recently I'm interested in understanding the immune system. Believe me, innate immune system, understanding about the innate immune system has been changed drastically. Please, we need to check. The 2013 Cell paper and then Science and Nature paper, our previous understanding of the macrophages derived from monocytes is all wrong. Okay. So, and there is a humoral immunity here. Kai and Weibo, he did this kind of experiment, and here IgM is generated, even the against pegylation, PEG. Okay. So the second injection, we are trying to produce the therapeutics. Then it should be, it can be injected several times. So that's the thing, not the nanomaterials themselves. The thing we need to be paying attention to. So all these things are summarized with the help of the Jonathan Lovell and I forgot the names, and Oxford and Feng Chen, Chen, and then especially Kai here. It's coming. Thank you.
We have time for one or two questions, if anyone has a quick question. Or I have just a couple, because I'm also thinking, of course, you're a clinician, you want to talk about clinical translation. I have one little question and a bigger one. The short question is, people in the nanoparticle targeting field have learned that in mouse models with subcutaneous tumors, there is this EPR, enhancement permeation retention, which is non-specific accumulation. Is there EPR in human tumors? Do people know?
Yes.
People ask me all the time, so I thought I would ask the expert.
Actually, that's a huge area of research. We need to get huge money from NIH or NSF or the Korean Research Foundation to find out. So we need to just kind of stable labeling with the radionuclides to find out. So there has been interestingly, the EPR was introduced 30 years ago by Japanese investigators. And after that, it's just to stay there. However, the targeting ligands, it became easy to produce the targeting ligands. There has become, again, the debate between active and passive targeting. Nano specialists, they don't agree. And control release specialists, they don't agree. So we need to just to solve that problem and become the negotiator, not MI6.
Okay, thank you. I'm not going to take any more time, but I do want to point out that this is a really important talk that you gave, especially to remind people to cut through the hype and to check. We really have to check and see where things are going. Okay, I'd like to introduce our next speaker, who is Professor Jan Grimm from Department of Radiology and Memorial Sloan Kettering Cancer Center in New York, who's done tremendous imaging in a variety of modalities, and in particular has been a pioneer in Cherenkov, although I'm not sure that's what you're talking about today.
A little bit.
A little bit, okay, anyway.
Okay, thank you. So thanks, Anna, for the kind invitation here. Even though I'm still, I think, jet lagged, I have no idea in what time zone I currently am, but I'll try my very best. The original title, I think, which she gave me was a little bit different, and I asked her if I could change it, partially because I wanted to talk about something else where we had a paper recently accepted, which came out online not too long ago, and I thought it also fits very nicely to the prior talk, so I named it, I like these mysterious titles, When Particles Meet, and I originally gave that talk internally once, and this was on Valentine's Day. So that's where the title actually is coming from, so I stuck with it. So I'm going to talk about radiolabeled nanoparticles, and there are sort of two themes here, and I'm going just a tiny little bit into Cherenkov later on. And Anna, if I'm going over the time, just wave, or Bernd, you have to wave because you're after me. So you all know lymphoscintigraphy, and you all know technetium sulfur colloids. These are nanoparticles. They're around 80 nanometer large, and you all know these images for lymphoscintigraphy finding the sentinel lymph nodes. Weibo Kai gave a nice talk, I think it was today in the morning or yesterday, see, I already forgot, on radiolabeling of nanoparticles, and there are basically 4 different ways of doing that. So one is the most commonly used, which is you just put a chelator on your nanoparticle, and then you add your radiotracer to it, and then it's on. And that's the question who was asked before, do we really know whether it is on or not, or are these guys detaching? Are they detaching here? Are they dechelating? Are they transchelating? Is the tracer lost and we're looking at an empty tracer without the nanoparticle, which secretly MI6-wise is already somewhere totally different than you actually think it is. Then there's chelator-free radiolabeling, and that's what I'm going to talk a little bit about it. Then you can do fancy things like neutron or positron or proton bombardment of your original material to make the entire nanoparticle radioactive. For that, you need cyclotrons and very big, very heavy, very large, and very expensive equipment. So very few people do it. And a little bit similar is the direct synthesis from radioactive precursors, which also is not that nice because then you've got radioactivity everywhere and it can get messy. So I'm going to talk about the chelator-free part here. So as I said, the challenge is that chelators aren't all the same, and they all don't hold isotopes in the same way. Zirconium, for example, you all know cannot be chelated by DOTA, so you have to use another one. Also, they require that you modify the surface of your nanoparticle. So if you have a clinically approved nanoparticle, now you put a chelator on there, it's not clinically approved anymore. And I basically went through the other ones as well, transchelation, so you got these alternate biodistributions when your radiotracer just takes another way and the nanoparticles, basically the tracer goes left and the nanoparticle goes right because they're already detached or transchelated. So it would be nice if you can get rid of chelator in total. And at the time there were a few reports, but they usually work with just one radiometal. And you also want nanoparticles that bind a whole variety of chelators for different clinical questions. And we found an answer in silica, because silica has nice pores, especially if they're amorphous and mesoporous. And we thought we could put this in there. And I think you said a one-stop procedure would be very nice. And this is what we basically came up with. What happens here is you mix the silica nanoparticles with your isotopes. You need certain conditions, 70 degrees. Then you spin the particles down and wash them, basically removing whatever is left and free radioactivity, and disperse them, and then you've got radiolabeled nanoparticles, silica nanoparticles. So it's mix, heat, separate the supernatant, and basically go. And we tested a variety of isotopes. They're listed here. We got a radiochemical yield of over 99% at that condition. And if you look at I know it's a very busy slide, but it combines it very nicely. Here's the oxophilicity of these metals. These are highly oxophilic. These are very little oxophilic. Here's the ITLC, which shows you that it's really, except for the copper, here's a little free peak, nicely bound. And here different radiolabeling conditions at various temperatures. And here is the serum challenge, also even going up to 70 degrees. And you can see that all these are stable over time, except for the copper. So even the therapeutic ones are staying on there. And the time scale changes here depending on the half-life of the isotope. So gallium has, 3 hours. And of course, here we are longer. But the copper we are losing over time, and copper is the least oxophilic one. And I get into that. So how did we test this? It's a very nice, easy experiment if you use the biodistribution. So for example, we all know zirconium is a bone seeker. So if you inject free zirconium, you get a nice depiction of the skeleton of the mouse. If you now inject the zirconium bound to the silica nanoparticle, all you see is liver. And that's what those particles are supposed to do. They're going to the liver, and you don't see any skeleton here anymore. Here's another example, gallium-68, goes to liver and a little bit gut, and here's a little bit bladder. Whoops. If you look again, here is it on the silica nanoparticle, again, liver. So based on the distribution, we know it's bound. So what about the copper, though? Usually I talk a little bit more about it, but for the sake of time, I put the 2 or 3 slides together into one. What a very good grad student, Travis Schaffer, who is actually now in Sam Gambier's lab doing his postdoc there, came up with is that we sulfonated the silica and got sulfonated silica nanoparticle, and the copper then binds nicely to the sulfur. And here you see an EDTA challenge of normal silica nanoparticles loaded with copper, and they lose over time the copper. And if you look at the sulfonated, they all keep the copper on them. And here the same for serum stability. If you look at the ITSLP, here you see that it's all bound, and if it's the normal copper silica nanoparticle without the sulfur, you see the loss here. So by using, and it's relatively easy to do, the sulfonation of the silica, we can now also do copper labeling. Now the nice thing is you can, of course, depending on the particle, but you can silicate a lot of particles if you want to. So you can create a particle with the right condition where you can use this method. And we also tried, which I hadn't put in here, you can pegylate this particle and you can still radiolabel it after the pegylation. And then with a peg around it, you have an even better bioavailability and can then do further tricks with it by putting any ligands on it if you so wish. So changing gears a little bit to one of my favorite topics, Cherenkov. You probably all know what Cherenkov is. So I'm not going to go into detail. If you have a charged particle which goes to a dielectric medium, you get the Cherenkov light, mostly known from a nuclear reactor here. It's the Oak Ridge reactor, which they pulled out of the setting. This is the reactor core, and you see a lot of Cherenkov light. Now Cherenkov, if it's in a reactor, you can see it very well. In biomedical imaging, it's a little bit more difficult, and this is just to remind me to tell you, it depends on the isotope. You have a wide range of intensities here. The spectrum never changes. Here's lutetium as the lowest one. Here's yttrium-90 as the best emitter, and this is all standardized to the activity concentration. So you're looking at the same amount of radioactivity in the well. And, oops, sorry. You can see over time we collected quite a few isotopes here, including arsenic, which is a very nice and very strong Cherenkov emitter. And what we can do with the Cherenkov, you can read that in various papers, and this is summer overlight, I don't know, but you can still probably read it. We can play around. We, of course, get a PET image out of it. We get the Cherenkov light out of it, and then if we put a fluorochrome or, for example, another fluorescent nanoparticle in here, we get a third signal, which is the emission of a dye, which is excited by the Cherenkov, and with that we have shown that you can, for example, look at metabolism or MMP2 activity by using a peptide which can be cleaved by MMP2. Here's a FAM fluorochrome on it, which does not emit any light because of electron resonance transfer if it's close to this gold nanoparticle. If it's cleaved, it's released, and you recover the fluorescence, which is shown here. The green curve is the cleaved FAM, and this golden sort of curve is the FAM on the gold, and this was mixed with FDG. And it's a much larger panel in the paper, but basically what we have here is a tumor which is MMP2 positive, and this is an MMP2 negative tumor. And we are seeing the MMP2 cleaving here, releasing the FAM, and the FAM is then excited by FDG, which was injected into this animal. So what you're looking at is the activity of MMP2 depicted through radioactivity with the help of Cherenkov. And the nice thing is, without going into further details, because you can do the PET and you know how much radioactivity you got there, you can do quantitative absolute calculations, how much activity of the enzyme you have there. Now, we did clinical Cherenkov. I didn't put it in here, I think. One of the problems is that the activity you see, as I said, is very low. So we need to image about 5 minutes. to get anything, which clinically can be done if it's a really nice dark environment. So we basically put the patients in a black box, literally where they're sitting, which makes it difficult if you want to introduce, for example, intraoperative imaging, because it's a little bit tough to get a room totally dark, and the surgeons nor the anesthesiologists like it a lot. So we're looking at various means to how to amplify Cherenkov, as it said here. And there are not many things you can do. One is you can inject more radioactivity. That usually doesn't play very well with anybody, including NIH. The second one is if you look at the Frank-Tamm equation, which is an equation describing the Cherenkov effect. And interestingly, I think Tamm was a roommate of Cherenkov at the time in Moscow. Cherenkov described the phenomenon experimentally, and then Frank and Tamm pulled after in the same lab and described it basically mathematically. Here is the refractive index in there, and it's to the square. So what happens if you increase the refractive index here going from 1.2 to 1.8, the threshold basically which describes the energy which is needed to generate Cherenkov light, the threshold decreases considerably. So here at 1.2, you need 600 keV energetic particles, subatomic particles, electrons or positrons. If you have 1.8, you are at below 200. So this is shown here. Here's nothing. Here's normal water, and then there's ethanol and salt water. You can visually appreciate that you get more light out of it. What can you do with it? If you decrease the Cherenkov threshold in tissue, which is around 1.3 salt water, so basically this here, you can gain in certain isotopes a nice effect, and in others you don't. So if you look at yttrium-90, the green curve, highly energetic electrons coming out there. If you're already here, this is the 210 keV threshold in tissue. So every particle needs to have a kinetic energy of 210 or more to generate Cherenkov. If you reduce for yttrium-90 that threshold, so you move this dotted line into this direction, you don't gain much. Maybe this little thing here, but there's so much already giving you Cherenkov, it's a very little gain. If you look, on the other hand, for example, at lutetium, which is the red curve, you get more if you move over. If you look at this purple curve, which is phosphor-33, barely gives you any Cherenkov, and if you move the curve over, you suddenly get one. And this yellow one is actually sulfur-35, which doesn't give you any Cherenkov, but if you move the threshold over, suddenly you get some light. So we thought, well, that's great. Let's find some nanoparticles which have different refractive indices. And we started with the silica. That's where the idea came from the radiolabeling, which I showed you before. And then we tried that out, and lo and behold, we saw indeed some increases of the signal. Here's a refractive index. This has a 2.1 hafnium oxide, and we saw an 8-fold enhancement. So we were excited, and then we plotted the refractive index over the enhancement, and there was no correlation at all. So no matter, and you can see it here, here's a refractive index of 2. Here's one of 2.1, so roughly the same, but here it's 1.6, and here it's 6 times. So there's really no correlation between enhancement and refractive index. Now, there was a paper in Nature Communication in 2015, which was a very nice paper, and they described radiopharmaceutical excited fluorescence imaging, or REFI. And basically what they showed here were Eppendorf tubes with FDG, and here they had europium oxide. And if you have those next to each other, you see that the europium oxide starts to luminesce. If you put a black box over it, so that means you've got no Cherenkov, there is no luminescence anymore. If you put an aluminum foil in between, which they say basically excludes any beta particle from passing over here, you still get some luminescence here. And if you put lead in between, you don't see anything. And this is just a repeat of the first. So they called it basically gamma ray induced fluorescence of these particles. And what we were wondering a little bit about is they put these at a distance of about, what's that, 2-3 millimeters, 4 millimeters maybe? And these are Eppendorf tubes. And they assume that they're here they block the betas out. The point being, at this distance, you don't have any betas coming over there anyway, because the distance is too large and you've got plastic in between. So there is no beta in this case coming over. So this is basically the concept of how particles getting excited. So as they say with the gammas, and then with the photons, and then you get the Refi gamma scintillation, and you get CRET, fluorescence, sci-fi, how we called it. And this is just a graph from Simon Cherry, which shows you the distribution of a positron, which doesn't go much more than a millimeter, from FDG, which was what they used. So here comes when particles finally meet. So we then started to look at beta scintillation in nanoparticles. But how do you look at beta scintillation? So what we came up with was that we used tritium, which just has a beta emission with 18 keV. So it's so low, it doesn't give you any Cherenkov. There is technetium, which mostly is gamma, 140 keV. There's some secondary electrons coming out, but they're very, very rare and very not that often. So basically it's gamma. And here's your sulfur 35, which also is a beta minus electron, and 52 keV, so it also doesn't give you any Cherenkov. So we have a pure gamma, the technetium, more or less pure, and then these two differently energetic electron emitters. And if you put these together with a range of particles, here's water, glucose, these are silica, titanium oxide, hafnium, gadolinium, yak, doped cerium particles, and europium oxide, you see that even though the tritium shouldn't give you any signal, you see compared to the water, which is here, this is what, 10, maybe 20, 30, and here you are at 20,000 or something like that. So you get quite a bit of enhancement, which is shown here. And that enhancement can come from Cherenkov because those guys don't produce any Cherenkov. So the only way that this interaction can take place is a direct interaction of the positron or electron in this case with the particle. Here's another example where you can see it nicely. Here's 35 sulfur. In glucose, you basically get nothing. If you use an europium oxide nanoparticle, you get this enhancement. If you use the same amount of europium, but now as ionic solution, so europium chloride, you get a little bit of enhancement, but by far not as much as in the nanoparticle. So you need the nanoparticle component in there to get this enhancement. So you might think, what does tritium or sulfur or does clinically? But here's some clinical radio tracers. And the same, here's water, glucose, silica, and these various nanoparticles, and the rare earth ones are the best, as you can see. And we get, compared to the water, always a nice enhancement of several logs, 2 logs at best. You'll see that here's no nuclide, and there's still some light coming out of these guys. The reason being is they are getting excited from light if they sit in the lab. So even if you try to keep them in the dark, you still have to take them out and pipette, which isn't always excluding any light. So some of them are luminescence by themselves, but even then, if you add the radio tracer, you get more light out of it. So here are the spectra of various nanoparticles, just if you put them in a spectrometer, and you see these various peaks at various widths and at various wavelengths. So what can you do with it? Here's imaging with a pure beta minus emitter. In this case, it's 32 phosphor. And we're using these different peaks, and basically what we have here is matrigel. These are the bismuth particles alone, and here are, you can read it there, they are mixed, either europium or bismuth with or without the phosphor. And if we put in a filter of 620, which is this peak, you see that only this guy here, that guy there, lights up with this, which is the europium particle with the phosphor. So we can spectrally resolve it, and we can go so far that we can do multiplexing looking at the various peaks. Unfortunately, we don't have one peak where we have the europium alone and no gadolinium, for example. But if you look at the different wavelengths, you can sort it out. So this is open. You look at everything, Cherenkov plus luminescence. Here's the 620 again. You can isolate this one. Here's the 540, which is only the gadolinium particle. So here you only you still get this area here, which you also see here, but you see that the europium particle doesn't do much on the 540, but it comes through at the 620 and in its other peak. If you do ratiometric measurements you can sort these particles out just by using 32 phosphor and electrons. Now we went further and looked at characteristic X-rays. Here's again the 32 phosphor pure beta emitter, and here is the pure gamma emitter, and we see characteristic X-rays coming out of these particles at, again, different kV, so basically different wavelengths. And of course, you can probably think what is coming. What we did is we did multiplexing with characteristic X-rays based on beta scintillation of the emitted betas in the particles. So here we used, what is this? Here we have the hafnium, here we have the europium and the bismuth. And so we did MSK, Memorial Sloan Kettering Cancer Center. We didn't do the CC, and looked at different energy windows. The problem we had, to be quite honest, is that down there to get really nice energy resolution with the scanner we had was quite difficult. And also to get a good calibration, because of course all these spectral and wavelengths are not even in any of the software you get from the vendors, so we had to create them on our own. Newer scanners, by the way, will have a much nicer energy resolution, so you can probably get much better results. So again, what we did is we did multiplexing. So here we're looking at europium particles, here at bismuth particles. Here is the mixture. Here you see the europium lighting up in the spect. This is the CT part where you see the dense nanoparticles. Here it's a little bit denser, but here you see the light coming, or in this case, the characteristic X-rays from the bismuth, and not much coming from the europium. So now you can basically image. But the reviewers asked, rightfully so, well, what can you do with it? Well, we looked at yttrium-90 thermospheres. Of course, what you can do with it is you can do Bremsstrahlung imaging, and we know that there's a certain amount of positrons coming out. But nevertheless, the Bremsstrahlung is relatively low resolution. They're very ill-defined. They're not very good, these images. There's this minimal positron, and those PETs don't look great either. So what we did is, here is no nanoparticle. This is CT. You see the particles in there. Here are the europium nanoparticles in one mouse, and you see now the characteristic X-rays. So you know, if you mix that together, where your teraspheres actually are injected. And here are the bismuth nanoparticles in another mouse. What we wanted to do, unfortunately, we weren't able to, because you can't buy these particles. You can buy them, but then they're way too big. They're about 300 nanometers, and we wanted to make them small and coated and everything. And we wanted to radio label them and then target to the tumor to be able to say, look, here's the tumor margin, and here are the serospheres, and you're right on target, or you're a little bit missing that corner of the tumor. Unfortunately, we couldn't just synthesize the particles as fast enough as the reviewers wanted us to do that. So we stuck with this. And we also did this experiment where we looked at sentinel lymph nodes. Here we injected, I think this is europium, this is gold. Smaller particle travels much faster. You can see this guy going up here, and this is still stuck here, and here's the injection site. And if you look at the 620, you can then spectrally, optically resolve where these particles are and look at the lymph nodes. This was another example you can do. And you can come up with all kinds of variations of the theme, where you can mix a radio tracer and a nanoparticle, and if they come together, you get a nice signal. You can actually then target certain entities and play this game further. Here's a little bit theranostic. There were papers around and about which said, hey, you can use Cherenkov light to do photodynamic therapy, and the Cherenkov will activate a titanium nanoparticle and some photosensitizer, and then you get reactive oxygen species, which it does. But what they sort of not misclaimed, but didn't recognize, is that there are also the betas, and that the betas probably do much more because they're so much more energetic than the Cherenkov light. So this is shown here. Here is 35 sulfur, which doesn't give any Cherenkov, but it does give positrons. And together with the titanium oxide and this transferrin receptor and the titanosin, which is in the original paper by Samachilifou's group, you can see that the cells are killed by this combination as well, and actually even better than radionuclide or for the FDG. This was what they used in their paper. Not the green stuff. This is the green, yes, but this is the sulfur. And you can see that even two agents which don't create any Cherenkov still induce photodynamic therapy, which is not really photo, you could call it particle-based dynamic therapy, if you want. So there's more going on, basically. And I think the gist of the story is really, we heard, well, we can radio-label nanoparticles, and we always thought that these radio-labeled particles are just inert and are just carrier moving on and moving the radioactivity somewhere. But they are not. So there are interactions between the radioactivity and the nanoparticle, which can create their own signal, which you can use. What we haven't looked at, but I think one should look at, is especially if you look at therapy, do these low energetic X-rays, the characteristic X-rays, have any effect or not? So here's a mechanistic summary. I think this is my last slide, if I'm not wrong. So you get all these various combinations. You can look it up in the paper. Here's the tritium, where you got electron hole combination. For the phosphor, you get, yes, in the particle, because it is higher density from the sulfur, you get chunk of light, but you also get excitation and relaxation, electron hole recombination, ionization. In the gammas here from technetium, you get these effects. So there's a whole variety of interactions which create all kinds of opportunities and challenges as well if you put radioactivity and nanoparticles together. These are all our funders. And in here are the people, especially this guy here, Chuck Pratt, who did most of the work. And with that, I thank you. And I think I'm in time, Bernd. Yes.
I don't know about you, but I think I have about 6,000 questions, and I need to read the paper. Do we have a couple of one or two quick questions on? It's really fascinating. It opens up whole new vistas of what we can code or decode.